Really, the whole point of reservoir computing is to do these in analog, where you're saving a lot of time and power over digital. If you're going to do them in digital computers, there are a lot of other ways to do the same thing. So analog, you've got the system you've got, and you work with the parameters. There are things you can do other than pure optimization to improve the parameters. I'm not going to talk about much here, but a lot of what I do is looking at how to do these reservoir computers better. So in this case, I'm going to talk about how to reduce the size of the reservoir computers using some time shifts. So once again, it's good to remind people what I'm talking about, because when I mention reservoir computers, people will get a lot of very different ideas from different fields. People think different things. So as we keep saying, we have some network of nonlinear nodes, and inside these little blue dots is some kind of nonlinearity. They're coupled in a recurrent network, which never gets changed. I have an input here from some system of interest, so I can drive one or all of these nodes. I also have a training signal that's somehow related to my input. I want to discover that relation. This is an example of an analog continuous network. I could also do this with a spiking network, and the same ideas will apply. So we extract signals from these nodes, make a linear combination of these signals to fit this training signal. And the output of the training is this set of coefficients. In the testing then, I have again the same network. I drive with some different signal, and I have a testing signal. I use these coefficients from the training to make a linear combination of my output signals to try to fit that testing signal. So my error metric here is going to be this testing error. How well do I fit the testing signal? So mathematically, I can write down my reservoir computer in a general form like this. R is just a vector of reservoir variables. Typically, you can see hundreds to thousands of these variables. F just describes the nonlinearity. A is an adjacency matrix, which describes how these nodes are coupled together. W is an input vector, which describes how this input signal S is coupled to the different nodes. Well, the nice thing here is this involves far fewer parameters than a neural network, and the training is just a simple linear fit. So a lot of the concerns with training of a recurrent neural network don't exist here. Because you don't need to train internal connections, a lot of the constraints in designing a neural network don't apply. And that means node types can be all different sorts of nonlinearities. And it means also we can build these from analog hardware, which means they can be a lot faster and lighter potentially than a digital system. So just a few examples of reservoir computers built from analog nodes. A common way to do this is to create an optical reservoir computer where we use a time delay to create multiple virtual nodes. There are analog electronic versions. This is not a digital simulation of an analog system. These are real analog circuits, and these can include things like memristors. Lou mentioned the famous reservoir in a bucket of water. There are examples from neural tissue or field programmable gate arrays and all sorts of other things that people have come up with. So there are a lot of rules for how do you try to make a good reservoir computer. A lot of them are just sort of conventional rules of thumb. One rule has been to operate near the edge of stability. As Lou was discussing, that's not always true. People will try to maximize the memory capacity of the reservoir. Well, this is actually not always true either. You want to tune the memory for a particular task. There is such a thing as too much memory, and Lou sort of showed that in one of his examples where you see too much of the input signal. Sigmoid activation functions are still kind of the standard in the literature, but that is not really necessary. Other nonlinearities will also work. There is an assumption that a sparse connection matrix is better. No one ever really explores why this should be true. I have looked, but that's another topic. And I find there actually are some good things about a sparse connection matrix, but there's some qualifications that you still have to be careful you maintain a strong interaction between nodes. Well, the final kind of assumption I'm going to mention is that And reservoir computer has to be high dimensional. We're mapping signals into a high dimensional space is pretty much what everybody says, and they claim that's why these work. So I'm going to question that assumption. One consideration is some rather smart people who unfortunately couldn't be here said that reservoir computers are not general purpose computers. They're universal function approximators. What this means is there's a lot of computational theory people will assume should apply to these reservoir computers. It doesn't actually apply because these are not general purpose computers. So I'm going to talk about how many dimensions do we really need. Let's talk about what I mean by dimension. The original way most people thought about dimension, we measuring something like correlation dimension. In that case, we take some object embedded in some dimension, we take a set of hyperspheres, expand about a point on that object. The number of points within that sphere goes as the radius of that sphere to the dimension d, where d is some dimension and the d does not have to be an integer. This theoretically, I guess, is justified, but it's difficult with real data, and it really only works for low dimensional data. It's very hard to get this relation to scale over very much of a region where you can get an accurate measurement of slope. So the false nearest neighbor dimension was kind of a remedy to this problem. We embed the data in d dimensions, find the nearby neighbors, then move up to d+1 dimensions. We ask, how many points are still neighbors? If most of the points are still neighbors, we increase the dimension and we go and show the number of points that stay neighbors falls below a certain threshold. The problem here is, where do you set that threshold? It's not always obvious. Sometimes there's a continuous decrease in the number of near neighbors. So, of course, I have to highlight my contribution. I'm biased because I did this, so I think it's the best method. But we can also use the properties of covariance matrices. We take some signal embedded, or this can actually be just a multidimensional signal, and we take a cluster of nearby neighbors on that signal. So I have n points in d dimensions. I'll create a covariance matrix from these points. I'll subtract the mean, set the norm to a unit, and then create a covariance matrix, which is d by d. I can compare this to the covariance matrix for a random process. I can look at the covariance matrix eigenvalues, and I can use those to indicate the probability that the embedded signal is just random in that many dimensions, and so that the embedded signal is anisotropic in d dimensions. I'm going to assume that means the signal, if it's anisotropic, can be embedded. I can't prove it, but as it turns out, this works quite a bit of the time. So you can adapt these covariance and false nearest neighbors dimensions for reservoir computers. I've done that in a few papers. These actually measure different things. The covariance dimension measures geometry. The false nearest neighbor dimension measures predictability. But if I look at both dimensions, this is for a reservoir computer with a lot of random parameters driven, I think, by a Lorentz signal, have false nearest neighbor dimension versus covariance dimension. And these two kinds of dimensions are fairly well correlated for that reservoir computer. So they're both telling me something useful about that reservoir, something similar. So in an actual reservoir computer, I can take a couple of different types of reservoir computers. Lou had mentioned one of these reservoirs of polynomial nodes. It's just a nice way to represent a general nonlinearity. Or I can do a leaky hyperbolic tangent reservoir computer, which is a very standard thing that people look at. I can increase the number of nodes in that reservoir computer. I can measure the false nearest neighbor or the covariance dimension, and I see both of these dimensions for more than about 5 nodes, those dimensions saturate. So even though I go up to 100 nodes, the actual dimensions of that set of data with all those different components saturates. It means that these reservoir signals, although it's a 100-dimensional space, the signals themselves live on a low-dimensional manifold. So do I really need 100 dimensions to represent these signals? Well, I want to measure the signal diversity in a different way. Yes.
I just have a question about what you just said.
Yes.
Is it right that basically if you pick the right nonlinear
Yes.
function, that the right answer is 3 from around 63? Right at the end.
You want to know if I,
What
just
the
for
equations are.
the people online, want to know if I picked the right parameters, that the answer is 3? You get these are two different types of reservoirs, and yet they give a very similar dimension. So it tends to depend on mostly on the reservoir. Even the input signal doesn't make a big difference. You're driving all these nodes with a common signal. So it's not surprising in hindsight that the manifold is going to be low dimensional. You can change the dimension some by changing the strength of the interaction, but you tend to get dimensions below 10 for most combinations that I've seen. Yes.
When you're using a scale to determine what negative is it a data-driven scale or is it an external scale?
This is a data-driven scale.
Like a variance matrix.
Yeah, I take that covariance matrix, I measure basically how many eigenvalues are outside of the expected distribution and set a probability. So if 98% of the time the eigenvalues are outside of what I expect for random data, I say, okay, it's 98% that this thing is anisotropic. So another way to measure the diversity of these signals that's useful is the covariance rank of those signals. And I'm not the only one who's thought of this. And I put a limber and all, I found done something similar, but I can put the reservoir signals into a matrix. I want to know how many orthogonal dimensions in this matrix. So I can just subtract the mean and normalize and find then the covariance from this reservoir matrix. The eigenvectors of that covariance are orthogonal directions. And I have found that actually the rank of this covariance is a useful measure of the diversity of the signals in that reservoir. So I should mention dimension versus rank, because I get confused, other people get confused between the two. Dimension and rank are actually different things. And the best example I can come up with to explain the difference is I'll take a matrix of signals from the Lorenz X signal. So each of these columns is the Lorenz X signal, but I start with a different initial condition for each column. So then these are just a series in time of the Lorenz X signal with a different initial condition. I can then take the covariance of this matrix, and the rank of that covariance is 100. So if I wanted to use a basis, it's 100 with a rank of 100. If I measure the covariance dimension or the false nearest neighbor dimension, those are much different. The covariance dimension is 5, and the false nearest neighbor dimension is 8. So yes. Yes. I can't quite hear. I think people online probably can't hear either.
So what I meant is like your solutions, okay. So I'm a bit confused with your notion of manifold here, because I feel like you're talking about deterministic dynamical systems, right? Mm-hmm. So that means it's like the solution may not necessarily lie on a low dimensional manifold, right? My understanding of manifold is something smooth like.
As you can tell, I'm not a mathematician, I'm an experimenter, but essentially there's some low dimensional surface in a 100-dimensional space, which is where the data lies. So I'll let the mathematicians figure out what I really mean. But
so the reason why I pointed this, I'm asking this is because your covariance dimension, right?
Right.
Had the object lie in a low dimensional manifold, the first d eigenvalue, it should point out to the tangent space, and the rest n minus d, it should be point out to the orthonormal space in the ambient. I mean, that's just basic fact. You just use, you can just use Taylor expansion on the geodesic coordinate to prove that.
That's fine, but I mean, the false nearest neighbor is not a geometrical measure, that's a prediction measure. And that says to predict the next point, you don't need all 100 dimensions. You can use a lower dimensional surface. So it's two different ways. Something about this data is low dimensional. So do I need 100 dimensions to get a good prediction? So I'm not very good I'm not very specific mathematically. I probably mangle the terms. I'm more of an experimenter. Okay, so the two signals I'm going to be using here are fairly familiar. I'm going to look at a Lorenz or Rosler chaotic systems for my measurement signals. I'm going to drive reservoirs with the X signals and train on the Z signals. The three different reservoirs I'm going to look at, one is a hyperbolic tangent map, so this is fairly common in the literature. I've got the polynomial ODE Lou also talked about, and a laser delay reservoir computer. It's three just very different systems. So looking at these different reservoirs with different signals, on this axis I have that covariance rank. On this axis I have the testing error, which is my metric for how well the reservoir works. I can use reservoirs of 50 nodes or 100 nodes, and the red and blue curves are lying on top of each other, which means that how well I can fit my signal doesn't really depend on the number of nodes, but actually on the rank. The number of nodes is important because it lets me get to a higher rank, but that's really all putting in more nodes does for me. It lets me get a higher covariance rank. So I should also mention memory capacity because that seems to also be important to people. This is a standard definition from Jaeger. There are some things I don't like about it, but it's what everybody uses. They want to know if a reservoir computer remembers a noise signal. So we drive with a noise signal and train by post-dicting the noise signal. So looking at the noise signal in earlier time to see how well we remember it. And the metric is really, it's a correlation between the output and the noise signal previously. What I don't like is in use the reservoir is not actually driven with noise. So this can produce some weird, spurious results. But again, taking testing error versus that memory capacity, I see for 50 or 100 nodes, the curves lie on top of each other. The only advantage of more nodes is it lets me get a higher memory capacity. You will notice some weird stuff here where memory capacity goes up, but so does error. In this case, the reservoir is actually going chaotic for the Lorenz or the Rosler driving signals, but not for the noise signal that you use to calculate the memory. So this is where the standard memory capacity definition doesn't really work well. So what I'm saying is the reservoir computer performance depends on the rank of the memory and not necessarily the number of nodes. So we want to increase the rank of our memory. Do we really need that many nodes? Can we increase those without the high dimension? And I should mention, I actually got ideas from this paper that had just come out. They used time shifts that were randomized and optimized to decrease the error in a reservoir computer. I used something similar to decrease the size. So the way I've used this is we take an ordered set of time shifts. So the reservoir has M1 nodes. I'm going to create M2 time shifts. Now, if we have M2 delays, but the reservoir has only M1 signals, for example, like this, I'll just repeat reservoir signals. So here we have time shift 1, 2, and 3. And then for time shift 4, I'll repeat the first reservoir signal and so on. So I'll just fill up this matrix and I'll use interpolation for non-integer time shifts. So both simulation and experiment, I'm going to use a laser delay system. In this case, we have a solid state laser. It goes through a Mach-Zehnder interferometer, which has a sine squared nonlinearity, then a delay loop, a photodiode, and an amplifier. We create virtual nodes here by time multiplexing. So we just sample this delay loop at different times to create our nodes. The nodes are coupled because in this amplifier, there is a low pass filter. So the node at time 1 or what time now is coupled to a previous node because of the low pass characteristic. So this looks like a one-way coupled ring network. And the node variables will be new, so I'll just arrange them in a matrix like this, so it looks like a reservoir computer. And this is fairly well known in the literature. So once again, I'll drive with X and train on Z signals from Lorenz or Rosler and create a time-shifted matrix. So this is the number of nodes in my laser reservoir. These are the three capacities: testing error, covariance rank, or memory capacity. This red line up here is the actual error for the laser reservoir with M1 nodes. So it decreases as I get more nodes. These lines are for my delay matrix with, there's 50, 100, 150, or 200 nodes. As I see, as I add to the delay matrix, I get a smaller testing error. In fact, here for about 20 nodes, I get a testing error that's about, factor of 20 lower. So I do, in fact, about 20 better by adding this delay matrix. So I could use a fairly small reservoir and get a fairly small testing error. As we see these lower two graphs, what's going on is a covariance rank and memory capacity are both increasing. You notice these curves all saturate. That's because, like for here, for example, once I reach 200 delays, well, I have 200 delays here. This matrix is the size of 200, so I can't have a rank any higher than 200 for a matrix with a size of 200. But the memory and the covariance rank are all increased just by adding this large delay matrix. So I can just keep the reservoir itself fairly small. That's fairly important for these laser delay systems because you're depending on this big delay loop to give you extra nodes. The more nodes you need, the longer that delay loop, the slower your reservoir runs. So this could give us a big speed up by a factor of 20 or so in that delay reservoir. See the same patterns if I use Lorenz to drive this system. And I see the same sort of patterns using different kinds of nodes. So this happens, it's not just this system. So this is the experiment. And I get this to work also for the Rosler and these squares, the red or blue squares, the Rosler just driving the regular reservoir or the Rosler with a delay reservoir. I can see adding the time shift matrix decreases the testing error, and the same when I drive with the Lorenz. So this does work in the laser delay experiment. So this could be an actual reservoir computer. So I know from work on nonlinear time series approximations, I think Eric Bolt was scheduled to give a talk here later, he does that the nonlinear part and the delay part of a reservoir can be separate. So you don't need a reservoir computer necessarily. But the same is true here. The reservoir doesn't require high dimensions. Adding that delay matrix doesn't add to the dimension. It just adds to the rank. And we can kind of guess this could have been true for measurements of low dimensional reservoir computers. So that's been published here where I show the actual reservoir can be low dimensional. You can add the rank into memory with delays. Thank you.